I, something like that. So here we are in, we don't know, maybe infinity, maybe something bigger. But we want something here.
Doctor?
Yes?
This is M or N?
They don't say n, yeah, thank you. This is n. And here should be something bigger than n. Right? Why? To look for better features, right? It's like we are selecting if you want, right? Selecting according to eigen value, right? What is eigen value? As we did last time, is the values. More the variance is big, more the data is, we have more information. When the variance is small, what does it mean? Less information. So it's not, we can cancel it. Okay. So the idea here, the trick of the kernel, we don't have explicitly these features. We don't need it. But we know that the kernel between xi and xj is just the dot. This is vector, right? This is value. When I have to put the transpose here or here?
What's there? The second
The first one. So the first one, what will be here? Row, colon, it gives me a value. So this is the idea here. I don't need it explicitly because all the calculation that we did in the PCA, if I do it again, we need always the dot product. So what does that mean? We don't need it, but we need the kernel functions. Clear the idea now? Now what I will try to do, I will try to find the eigenvalue and eigenvectors for the new space. How we did in the, how to find the eigenvalue and eigenvector for the, without kernel, the normal PCA. Which one we did do? We have to calculate the covariance matrix.
We can write phi and phi transpose after that.
Let me try it again. We have phi of xi times phi of xj. We call it kernel of xi xj. Here, by the way, I can't change the order. ij, it is symmetric, doesn't matter. So what is your question here?
Yeah, we can replace the places of these. We can write transpose later than phi xj before. Phi xj before.
I think if the question means, can we swap it to me?
Yes, yes.
If we swap it, it became a coming. This is value, right? Okay, I'll go to it. How to find the matrix, the covariance matrix? What is the formula, please?
X minus
1 out of n? What is it? Okay, we suppose everything is symmetric, okay?
Yes.
If it's not symmetric, the mean is 0. If not, we have to subtract, as I told you last time. So we suppose here the mean is, how to find the mean here, please? The mean of this one.
X minus
x1 plus the sum of xi divided by n, right? Okay. We suppose that it's 0, right? What should be the covariance matrix here, please? This one I call it capital X, right? If I put index, mean is vector. Without index, mean is matrix. Just one agreement. So what will be here, please? X times x. Why you have to put the transpose? First or second? This one is matrix, n by n. So it should be in the second one, right? Clear? So the dimension should be m by n. If the question, for example, I give you a matrix X, but I will flip it like this. X1 until xn. This is my X, right? What should be the dimension here? N, m. So in this case, what is the covariance matrix? X transpose with X, okay? You have to have m by n, number of features, okay? Doesn't matter, I can put it in different way, the matrix, okay? But let's agree always it's like this, okay? But in case, be careful about it, okay? So we need to find for this one, what we need to find? The eigenvalue and eigenvectors. So now the problem here, this one I call it capital phi of capital X, right? Mean is matrix, okay? So this one we call it this one. So what is the covariance matrix here? I call the covariance matrix of the new space, right? This is normal one. What is the covariance matrix here, please? Same thing as we did, n phi x times, because I have to have like the new number of features double, right? Clear. So now, but this one I don't have the phi, right? Yes or no? But here to find the eigenvalue and eigenvector, I will show you in a few slides that it is related to the kernel matrix. So the kernel matrix, can we calculate it or not? We can, right? So we don't need to know explicitly the function phi. So I will prove later on that the eigenvalue and eigenvector, a certain constant, are the same, covariance matrix or the kernel matrix. Okay? So this is the idea only. Nothing difference between the normal PCA and here. So here we are going to big space with different function of phi or kernel, and the kernel can be any functions, polynomial, exponential, whatever you want to do. But here, the idea about kernel, what is kernel, please? We say kernel between any two vectors should be function of this one, right? Any function. You can put exponential, we can difference, polynomial, whatever, as we did in the previous week, the last 10 minutes. Clear the idea now? So, let's go slowly. So this is symmetric. So this is mean dot product, doesn't matter. So sometimes if I write this one here, no, let's do it, let me write it again here. Fine. So usually if I put x times y, it is exactly like, or it is the same thing like, so dot products or inner product or matrix product is always give the same thing, okay? Just the way to write it, different, doesn't matter, okay? So the inner product, matrix product, dot product, but give the same value, right? Okay, so look here, this is matrix, it is symmetric or not? What do you think? Yeah, symmetric, right? Everything are the same. Based on this, so we can say this, the matrix is symmetric. Take example here, find the kernel, we have x. So we suppose x1 is here. Do you agree with this calculation or not? Sometimes I put a typo, right? So the kernel here, it is, look here, the kernel xi, xj is 1 plus xit, xjt to the power 2. And this is, we did it last time, that we can find phi explicitly, okay? In this specific case. So now we want to find the kernel function. How to do it, please? What is our matrix X? We have x1, x2, x3, right? Yes. What is the value of n, please, here?
3.
So number of column is n, 3. M, they are the same in this specific case, right? So usually he just gives small idea. Okay. So how to find a kernel matrix here? If you want to write it in matrix product, so we have phi of x is this one, right? Okay. So what is kernel, please, here, please? How to calculate? Is it the same thing we do, only the ij, right? 1. What is it here? 1 plus xi, xj power to the power 2. For example, if you want to find 9, what is 9, please? 9 here. The first x1 with x1, right? Yes or no? What will be here? Let me do it here, maybe you can get it. So please, can you tell me what is k of x1, x1? What is it? Is 1 plus x1, x1t to the power 2. What is x1 here, please? This one itself, right? So it should be 1 plus 2 square, which is 9, yes? So my k matrix is n by n, so it will be here is 9. Let's do another one, for example. K x1 with x3. What is it, please? Is 1 plus the whole square. x1 times x3, what is it? x1 times x3. Minus 2, minus 2, minus 2, minus.
Minus 4.
So it will be again is 9. So we have 1 with 3. Here 9. By symmetry, the same thing is 9. Clear? Sorry? Here is okay, this one? Can you repeat again? Okay. Okay. What is x1 and x1, 3? What is it, please? What is x1, please? Is minus 1, 0 and 1 times 2, 1, minus 2. What is product here, please? Minus 2, 0, minus 4. I just put it here. Because by definition, this is kernel. Okay?
I'm saying that 4 plus 1 will be 5, 5 square root of 5 is 4 plus.
But minus, huh? 1 minus. 1 minus 3 minus 3 square is 9. Clear for all? How to find the kernel? Or if you want to find the so here it means is product, right? See here, is product here. Here is, you know when you do the programming, a matrix times another matrix, but element by element, not matrix product. Okay? How we do it in MATLAB? When you have the matrix, we put dot star, I think, right? Mean element by element. Okay? Yes.
So can you just repeat the
This one? So here what we have, this is the normal features, data. I do the kernel, and we get another space with more features. So we want, but this one we don't have it explicitly. We need to find only the kernel function. So I'm calculating the kernel. So the kernel should be given, which kernel we are applying. In this specific, we apply quadratic, we call it quadratic kernel, power 2. If we have any two vector, you do the product, you add 1, multiply by 2. So for example here, I apply between 1 and 3, between 1 and 1, I'm trying to fill the matrix. So we can do 1 with 2, with the same thing here, and 2 with 2, 2 with 3, 2 with 3, and 2 with 3. And you fill in gap. You'll find at the end is your matrix here. You'll find this one. Do you agree with 100 here? Maybe is it not typo? Do you agree with 100? 100 I mean 3 with 3, right? 16 plus 81 plus 1, the whole square plus 1 and all the square. Is it correct? Is it? Let me check it here. 3 with 3, what we have? 16 plus 1 plus 81. You agree with that? Yes or no?
No.
3 with 3, right? Yeah. Let's do it together. Let me do it again here. 3 with 3, what is it? 3 with 3, 3 with 3. What should be the value here, please? 1 plus. No, sorry, actually this first one, yeah, sorry. 4 plus 1 plus 4, right? The whole square, it became 10 is 100, yes. Thanks. I took the other one. Correct? Clear for all? Okay, let's do it for the another kernel. I will do this one here. We call it Gaussian kernel, or another name. It is k xi xj is exponential minus 0.1 the Euclidean distance. Can you try to do it all, please? Can you just check 2 or 3 elements for this with this one? Usually we call it Gaussian or RBF kernel matrix. A lot of people they use it.
Doctor,
Yes.
how you got that 100? I guess minus 4, 1.
Okay. Can you do x3 with x3, please? The product.
Yeah, it will be minus 4 multiplied by minus 4 is equal to 16 plus 1 plus.
No. Okay. x3 with x3 with itself. 2, 1, minus 2. 2, 1, minus 2. Together. 4, 1, 4. Yes? Plus 1 here, yeah? Okay. 10 square is 1. Yes? Ah, yes, good question. What is the size of K here? N by N. Yes, it is not covariance matrix. Covariance matrix is M by M. Okay? So here K is N by N. So please, can you check this one here, please? Let's try with x1. So here, everything x11 or K, x1, x1, x2, x2, x3, x3, the distance is 0. Exponential 0 is always 1. You see here 1, 1, 1. It's clear. Let's do x1 with x3. What will be here? Exponential minus 0.1. What is the Euclidean distance between x1 and x3, please? x1 and x3, what is the difference? Minus 3 and 1. So it will be here. Minus 3 squared plus the difference is 1 or minus 1 squared, doesn't matter. 1 minus minus is 3 squared. So it will be here, exponential minus 0.1, 9, 10 times 19. So if you do the product, you will get 1 and 3, 0.149. Is it clear here? Or calculation, right? So here, whatever you can, here we can do for polynomial, we did for Gaussian, you can do any type of kernel. How to find the kernel matrix. Why kernel matrix is important, I will show you later on that we, in order to find the eigenvalue, the eigenvector, we use the kernel matrix. We don't use the yes.
Sorry, I don't get where this 0.1 came from.
This is the definition of the Gaussian kernel, by definition. 0.1 times the Euclidean distance between xi and xj. When you have xi and xj, just put the distance square, nothing else.
The 0.1.
This is by definition. You can do 0.5, whatever. It's just parameter, yeah. It's parameter. It looks like a Gaussian distribution, one out of variance, and one out of two variance, if you want. Yes.
I mean, like when we have 3 cross 3, I mean 3 rows, 3 columns, then how can we get the 4 values? 1 plus 4 plus 1 plus 4.
Okay, let's do it. Let me do it slowly.
Because we have 3 cross 3, so it should be around like.
Okay, 3, 3. Okay. What is x3, please here? Can you tell me what is x3? Is
2, 1, minus
2, 2, 1, minus 2 times 2, 1, minus 2 to the power 2. What is it? 2, 1, 4. Yes? So when I put x3 is the entire vector.
Alright.
Okay? Clear? So the kernel xx is the dot product, but in the new space. So please, phi of x, it's just a new vector, so don't be scared about it. Just put phi of any vector. It's like you have a lot of extra features, like this, okay? Put it in your mind, it's like, it's a new features. We add more features, that's all. We call it phi. So now, if we want to calculate kernel xx, we do the dot product, which is the norm square, yes? So the distance or the norm in the new space is square root of the kernel, right? Clear? Okay for all or no? You remember when we multiply x times x, always x square, right? So the same thing here. We have, when we do this one here, mean the norm square is this product, and the modulo for the new space is square root of the kernel. Example here, if you have x2, 3, what is the norm of this one here? What is the norm of x? So I'm just preparing you to get ideas. Okay, what is x here? 2 and 3, right? What is phi of x? What is phi of x? I don't know. What is k of xi, xj? By definition is, sorry, xi is 1 plus xi xj t squared. This is the quadratic response, right? So now, if I ask you, what is the norm of x here, please? The norm of x is square root of 2 squared plus 3 squared, right? What is the norm of this one here? I have to put something square, something square, something square, something square, but I don't have it. But we know that, what is the norm? Is just, do you agree with that by definition? Yes? This time this, right? Because here I can put it the same way here. What is the norm of x here? Is xt times x, right? Square root. So the same thing, the norm of this one is this, and this by definition is always please kernel, don't forget. Okay? And how to find kernel? I'm using the quadratic. What is it here, please? 1 plus xtx. What is x in this case? In this example here is 2, 3 times 8, 10. What will be here? 1 plus 4 plus 9, the whole square. Sorry, under the square root, what will be here, please? Sorry, because here there is square, I forgot it. So it will be here is 15 or 14, no 14. Clear? So please, when we add the norm in x, it's directly. When you add the norm in the new space is kernel. Why we use kernel? Because sometimes it's difficult to get the new space explicitly. As simple as that. Clear? So this is the only trick about it. A distance, yes.
It's not 15.
No, 9 plus 1, 10. 10 plus 4, 40. You did the same mistake, I worked with 15 too.
Actually, there is one in the formula.
Yes, there's one, yeah.
There is
Yeah.
one.
Yeah, we can remove the formula, right? Yes. If you remove the formula, look at, if I remove one and I remove two, mean we are getting back the same same space. There's no difference. Yeah, just to give it. Yes.
Wrong manipulation of that formula.
Wrong?
B 1 plus b square. A plus b whole square. We have to follow that rule.
Yeah, it is specific here. No, mean if I want to do other kernel function, kernel. Create other kernel
The
function.
formula that we opened will
No.
become here a plus b square.
It's not open.
I mean that the 14 is not the answer here, I guess.
Why?
Because our value is 1 plus 13 square root, then whole square.
And we have square root of the norm.
Oh, okay.
Yes, got it? Yeah, because the norm is square, right? Good. Okay, now let's find now the distance. What is the distance here? If we have two vectors here, for example, another vector here, 1 and 3, what is the distance between them? We do x minus y, the all square, right? Distance here, right? Here, what is the distance here? Same way, we do 5x minus 5y, but what is the distance? It is not square, right? Let me do it in matrix way better. Okay, so x minus y, what is the distance here, please? It's x minus y transpose times x minus y, right? This square, we do square root, right? Yes? Now we are going to the new space. What is the distance of this one? What distance here? Same thing we do, square root of times t. Yes? Correct or not? Okay. But this one here, how to calculate this one? I have to do the can we do decomposition here or not? I'll do it other side. Try to follow me, please. Are you following, please, what I'm doing? Is it not difficult, right? Just how to do the distance in the two spaces. Okay. So what is the distance here, please? phi x minus phi y. So please, can you help me to do the decomposition, please? So what we have here? Can we do decomposition here? Phi t of x minus times phi of x minus phi of y. Clear? We do this one with this one. What will be here, please? This and this, what is it, please? Phi, which is kernel of x, yes or no? This with this done. This with this, what is it? Minus kernel of xy, yes? This times this, minus kernel y, x. This and this is plus kernel y, y. Kernel xy or yx, we can't add them because it's symmetric, right? So what will be at the end? Kxx minus 2kxy plus kernel of y, y, all underscore, which is exactly here what we have. So you have to always be careful when we're talking about distance or modulo in the old space or in the new space. It's different.
Is it okay? Here is minus 2kxy and here is minus 2.
Yeah, minus 2.
Yeah.
Yeah, correct. Why? It comes from here because it's symmetric, right? The product is symmetric, so we can change it. You can put here xy or yx, doesn't matter, same thing. Okay, so here we can create a similarity measurement. Example like this, I just apply it. Okay? I don't go in details.
Why do we know, like when to put square, why we didn't put square?
So usually a kernel here, I put it in bold, this is will be given to you. Okay, this is given. Okay, I will tell you it is which type of kernel it will be given to you, of course. Yeah. But for now, just put as k only.
This is a fixed rule of kxx minus kxy.
Here? Here is okay, correct?
I mean, when we expand, we get this always.
Yes, always, because if we do this with this, this with this, we have 4 factors. Okay, until now is correct here? And here? Here, because kxy or yx, it is symmetric. You see, for example, look to the bold here. If I put here, look here, x and y or yx, the product is the same thing, give the same value. Yes? Okay, so here, I just prove it here, what I did. Now we can use the cosine. You remember what we did before? So please tell me if I'm going too fast, if I'm just giving a basic idea. Okay. You remember what we did last time? What is the dot product between x and y? Which is xty, right? Or it is ytx. Same thing, all. How we can write this one here? Mean x times y times cosine the angle between them, right? So the same way here. Phi of x times phi of y. What is it? It's kernel xy, yes or no? Yes? Equals to what, please, here? The modulo of phi of x, yes? Times the modulo of phi of y times cosine, yes? But the angle here and the angle here are not the same. The angle here is the old space and the angle here is the new space. I can put it like this to make a difference between. Now, how to find this one as kernel, please? What is this one as kernel? This is exactly kernel xx. We just prove it now, right? What is this one here? Kernel y1. And just you can isolate cosine, you will get it here. Okay? So this is here in kernel and this here. Because this one we don't have it all the time. You cannot calculate it in the red one. We have to use the kernel to calculate only the blue one. Okay? And here examples. Here's the same thing what I'm doing. Okay. Look at now we go back to the things. We have the covariance matrix. Let me write it all here. Okay. Look, please. What is the mean of the new space, please? So please focus with me here in 5 minutes. It's important for the whole kernel PCA. Okay, what is our space now, please? I will call it phi of x, which is phi of x1 until phi of x n. The size here is n. The size here is n prime, the new features, right? And usually we want it always bigger than n. Yes? What is the mean value here? I will call it the mean in the new space. What is it, please? We add them, divide by n, right? The same thing. 1 out of n, the sum of phi xi from 1 to n, right? So, how we can write it in terms of matrices, please? This one, if you want to write it in terms of matrix, 1 out of n, phi x times 1, 1, 1, 1, 1, 1. What is the size of this one here? N times 1. Clear? Yes? If we do this one, we have the matrices. Mean is our mean value. Clear? Okay, mu. Is it in the new space or the old space? New space. So if I want to find the norm of phi, how we do it, please? Is kernel of? Do you okay with that? Yes? Or, but this one, the kernel matrix, I have only for xi, xj. So this one, I don't have it. How to calculate it? We go back to the definitions. What is the definition here? Phi times, where I have to put the transpose, first or second?
The second.
Okay, let me remove the square to put always square, doesn't matter. And this is the first one, right?
This is a matrix, right?
Who's symmetric or not? This is modulo is always a value. Clear? Because it's modulo of the vector, length of vector. Do you agree with that? Do you agree with that? What is phi here, please? I can use this, or I can use this one. Doesn't matter, right? Let me use this one here. So here I just put it like 1 n times 1, right? So what will be here? 1 out of n, the transpose of the first one, phi xi times phi of xj. Since we have two summations, I cannot put I, right? Because it's different for every index. I can put I and j. You okay with that? I missed something here. What is it?
N square. 1 by n square.
I put 1 out of n squared. Thank you. Yes. Another thing is missing. What is it? The transpose is here, right? Yes? Clear or not?
Yes.
Okay. Do the product here. Do you think we get this one or not? Yes? And look at this times this is the kernel xi, xj, right? And do double summations, yes? The double summation, what does it mean? I'm adding the entire kernel matrix. You remember what is kernel matrix at the beginning that we calculated? What do we do? We add all, look at all the elements of the matrix, kernel matrix, K. All of them. To add it, we can write it as a matrix product is 1 transpose K 1 over 1 n squared. And here is our modulo of phi. Is it clear or I repeat again? Okay. Okay. Do you, okay, until here, please, here is okay, right? This is our definition. Here, is it clear?
Yes.
I'm just coming. This is okay here?
Yes.
And dash.
No, no, just let me, until here, first one.
Yes, it's the first one. And
Here?
greater than n. Yes, sir.
Yeah, here the new number of features usually is bigger than the old features m.
So why?
Yeah, why we do this one? Let's go back to the source. Why? Because usually when we did, sometimes the shape of the data, it is not linear. So it is something, remember when we did the circular?
Yes.
So if you do the circular, you will get the covariance matrix, the same eigenvalue. So we cannot cancel each one. So what we want to do now, in this case, I want to go to another space. It's good question. What do I want to do? All this work in order to go to another space If I do the eigenvalue, I will find big value, eigenvalue, and others are all 0, 0, 0. This is the perfect what we're looking for. You got the idea? So to do so, we're getting to the higher space when maybe most of the eigenvalue are small. This is what we are targeting.
Doctor, I have a simple question.
Yeah.
Apparently, we are mostly trying to reduce the number of features.
Yes, correct.
And here we do augmentation. Instead of reducing, we do adding some more and more. So
Yes,
what's
but
the-
we did it because when we apply on the given features, we cannot compress anymore. So let's look to the problem on different angle. What I mean different angle, different space. You remember for the, let me go back to the circle, look at this one here. Can we compress it here? The data here, for example, the data are all here, please.
No.
So if you do the eigenvalue, I will find eigenvalue 2, 2. Same. This is on x and y, yes? You can't compress, right? I will go to the higher features. One of them, for example, is r. Here, if you give me r is enough. I don't need x and y. So I need only one features. What does it mean? I want to a polar coordinate, another space. So the same idea here. We can go to, for example, some people working on the wavelet, curvelet, Fourier transform, cosine transform, whatever. You go to other space and you look, maybe you can find better idea. You got it? So now we're going to do something bigger, right? Or if you want to, you can do something different, maybe small one, but it will be a better space. Clear now? Second one is okay. I have new space, new features. We do the mean. The mean, I can write it as a normal definition in statistics, or I can write it as matrix product. Clear? Now, going to the norm of the mu. Mu we are here, right? So the norm of this,
Why you took the mean?
sorry?
Why you are taking the mean?
Why we take the mean? Who can tell me why? Why we looking for the mean? Because I want to do the PCA on the new space. To do the PCA on the new space, I need to make the data centered as 0. You got the idea? It's very important. Clear or not? So kernel is just a PCA on the new space, nothing else. Okay? So is it clear? Second line? Okay, third line, I want to get the modulo, right? What is the modulo is? This times this, yes? What is the mean? Is this one. I just put it here, and I put it here. Now I do the product, yes? What is the product here, please? Mu phi, the modulo square is 1 over n squared, the sum over I, the sum over j, xit phi xj. Yes? What is this one by definition? Is kernel function, right? Yes? What is k as we defined at the beginning, please? What is it, xk? Is k x1, 1, right? Until kernel of x1, xn, right? Until k of xn, xn, right? So what does mean this one here, please? We add all the value of the kernel, that's all. How to write it in matrix equations? 1 over n squared, 1 tk1. You can try it if you get it easy way, okay? You add on the line, you add on the column, and we add all of them. Is it clear? So we prove the mean of this one, right? Yes.
Why didn't you take the square root in this one?
Excellent question. She said, well, we didn't take the square root as the Euclidean and that's it and finish done. We don't need to. But all the questions is, we don't have the vector here explicitly. All this one, we don't have it. So this is one. We do all this one because we don't have it. But if you are able to create a normal features extra, you go back to the normal fixed. As you have a new data and you apply to PCA of it.
Doctor, I thought that we are taking n squared because there is 2 mu. Mu transpose n squared.
The square here, right?
Yeah, I thought we are taking n squared because of these 2 mean.
Yes, square. Of course, yeah. This is true. No, she said we take here, for example, what is the model of this one? The first coordinate square, second coordinate square, and the square root. But we don't have it. For the Gaussian, we don't have it. Polynomial, yes, you can do it. But if I give you polynomial of degree 10, to find explicitly phi, it will take you 3 hours to finish it. Yes?
So why is it difficult to find the space here than
Why phi is not defined, right?
Yeah, I keep saying it's not.
Exactly. Let's do an example here. Let me give you real things. Okay. Exponential 0.1 xi minus xj square. This is your this is your kernel, or means is phi of xi times phi of xj t. This one is. Can you please tell me what is the vector here? You cannot. It's so difficult. So this is why we cannot here. So if you to find, can you find me two vectors? If you do the dot product, it will be equals to exponential of this. So first of all, exponential, we do Taylor series. Taylor series give me polynomial of degree infinity. So to do this one is very hard. It's very challenging.
And this is to solve which problem?
This one, because we are trying something non-linear, I try to make it as linear.
Don't we have other?
And you have infinity of kernel. Until now, every day, every week, there is researchers, they do a new kernel functions. Yeah.
I mean the non-linear, which is like x squared plus.
Yeah, of course, yeah, of course,
The
yeah.
same, like we're trying to find this one.
You can, yeah. But this one we call it handcrafted features. You are doing by hand, one by one. But sometimes we're looking to the function as exponential logarithm. So it is not really, we don't need to go in details. We go to something really huge space, and most of them we can compress it. So here, to find y, just here, take this one here. Can you find two vectors? The dot product equals to exponential of this. It's really hard. I didn't try, but maybe it's impossible, I think. Clear the idea? So now, the mean is fine. We go to the modulo is this. The modulo by definition is this. This we don't have it. Let's apply the kernel trick. The kernel trick here, the product is k. K is the sum of that or nothing else. Clear? Okay. So now I will try to make the data centered as 0. What does mean centered as 0? Every vector, I have to subtract the mean, right? But if I subtract the mean, the kernel will be changed. Yes or no? It will be another kernel. By definition, is this. And this, you do this, you multiply. I let you to do it at home, okay? You will find at the end, the new kernel functions depend on the old kernel functions, right? Just to make your data center. Okay, the proof is here. I will not go. I will give it to you later. You can read it. Okay.
So why we are trying to do this? Why we want to center?
Why? Because we want to go to a new space, and the new space, the calculation is different than the old space.
No, I mean in the new space cannot be in other, not in the center. And why you are keeping in the center?
Exactly here, because as I said, if you do the covariance matrix in the normal data set, for example, all the eigenvalues are the same. So there is no way to compress. There is no way to cancel. So what does it mean? Your data is not linear. So this is only what we have to do. So is it clear, please, why we are doing kernel or not? It's really important. So we are doing it when kernel, when PCA does not work well. I mean, all the eigenvalues are important. We cannot remove them. So I'm trying to look to the data from different angle or from different space.
But even in the VCR, we are shifting the data from the center.
Sorry?
In the VCR, if I remember correctly, we are shifting the data from the center.
We doing why we do your question? Why we shift it, right? We shift it only to when we calculate the covariance matrix. It will be easy for us. That's all. That's all. Nothing else. And also, of course, because if we are looking to the vector, and vector does not depend on the positions. It depends only on the directions. Because we're looking for the eigenvalue, right? Eigenvector, eigenvalue doesn't depend on the positions. So it's better to, if your space is here and this is your origin, it's better to just work here, not to make things simple, nothing else. And later on, when you find any value here, go back to the origin references. It's just to make the way of writing equation simple, nothing else. Clear? So this is the main idea here, okay? So I did 50 minutes just to prepare for this slide, please, okay? So now, we are looking for the eigenvalue and eigenvector for which matrix, please? So please look to this one. It's like a normal data, right? Just I call it phi is vector, right? If the phi bother you, just call it y1 and yn, nothing else, okay? Just like, okay, what is the covariance matrix here, please? I call it here because it's a new space, right? A by definition is 1 out of n of what, please? I have to have a m by m, like m, okay? Or m prime by m prime, right? What will be here, please? Same thing, phi f times. Is it clear, right? Yes. So now I'm looking for the eigenvalue and eigenvector for this one, right? Clear? As we did in the normal PCA. Okay. What we need to do now? I need to find what is the. I think you did with Nasreen and Abu Bakr, how to find the eigenvalue and eigenvector, right? If you have the matrix here, we multiply it by vector, should be equals to this one, right?
Yes.
So here, just by looking for the principal one, I put 1, 1, 1, and this is my phi. Clear? I want to get which vector and which eigenvalue satisfying this equation. Clear? Okay. Okay, so what does it mean here? This is phi. So now I need to multiply by vector u1. I need to multiply by vector u1, and I have to get lambda 1 u1. Clear? Yes? Okay. So what you can observe here, please. Okay, this is the product here. I can write it in different way. Do you agree with that, please? This is exactly 1 out of n. The sum of I, 1 out of n, phi of xi, phi of x, j, u1, right? So xi, no, xi is t on this one. Yes? So the way when you do a matrix times another matrix transpose is the same thing we do column by row. Same thing. You can check it, please. What will be here, please? Lambda u1, right? Please here, what is the dimension of u1, please? Dimension of u1. Any idea? Dimension of u1.
1 by n.
We don't have m here, m prime. So what is the dimension of this one here, please? M prime times 1. It is vector, right? Please, clear, right? Okay. What is the dimension of this one, please? Same thing. M times 1, because it's single one, okay. What is the dimension of this one here? M prime 1. Oh. Clear, right? Because we have M prime, and what we have here? N. Okay. Can you observe something here, please? So here's the key point. What is here, please? Here? What is the dimension of this one, this product? Is it value vector matrix?
M by n.
So it is m by m? You mean m prime, without m. M prime by 1? What is it? It is value or vector or row or column or matrix.
It's value, right?
Is value, thank you, is value. So this is value. Here it is a row, colon is always a value. Okay. So a vector plus vector plus vector plus vector is a vector, right? So what is U1 here? U1 is a vector. I cannot find it explicitly, but I can find it in terms of linear combination of phi of x. You got the idea? Can I divide everything by lambda? Look here, the n here, I will put it here. The lambda here, I will divide it is here. So it will be the vector u1 is the sum of this. So I'm writing, because u1 I cannot find it, because phi we cannot have it explicitly. And this is the same dimension. We don't know number of new features. So u1 is the sum of this. And this is the idea. And this we call it, all this coefficient now, sorry, all this one I will call it Ci, which is exactly here. So u1 is the sum of Ci phi of x.
Doctor,
Yes.
the dimension of this product.
Which one? This one?
Transpose U1.
This one?
Below.
Yeah.
This one. Isn't this m by m?
No, one by one. Look here. What is transpose?
The transpose will make the matrix.
Look here. The transpose, the dimension of phi is m prime times 1 transpose times the second one is m prime times 1. If you swap it, what will be here? 1 times m prime 1, m prime, it will be 1, 1. So it's value. Clear? You can look to it as row, column is value. So I want to just to understand that and now the eigenvalue u1, it is linear combination of this. But the problem is still there because I don't have phi explicitly. Yes or no? Correct? But usually for me, when I do the projections, as we did last time, because I need the main directions, but later I do the projections. When we do the projection, we are dealing with the kernel value. So we don't need it real explicit. Anyway, look here, for example, here now. So is it clear now? Yes. U is the vector, eigenvalue. Where is it? This is lambda. This is U1 equals to this.
You say we can't find it explicitly, that's why we need to shift them on the other side.
Yeah, of course. Until now, I want you just to understand that U1 can be written as linear combination of phi. What is the constant is this.
They have another U1 in the same equation.
Yeah, of course, yeah. You with you, yeah, still, yeah. Okay, I cannot find you until now. It's linear combination, but this is like a projection of it. I'm coming to this one. You see this one. So the Ci is just, look for example, please. If you have x, if you have a vector x, and we want to do the projection on phi of x. This is my new vector x, and this is my direction u. What is the unit? Is unit vector, right? Always. Remember eigenvalue. Yes or no? In the PCA, the eigenvalue always should be the unit vector. I mean the modulo is 1. So what is the projection here, please? As we did before, right? What is the projection here? So this one we call it a projection of what? Of phi of x over u1. What is it, please?
U1 transpose. U1 transpose.
Okay, for sure it will be the direction of u1, right?
Yes.
Yes? What is its modulo? u1 transpose times phi of x, right? Or you can do the transpose the other side, doesn't matter. Clear? This is value or not? Value times the unit vector. If you want to write it as matrix product, what is it, please? Phi of x, u1, I put u1 is here, and after here u1t, phi of x. And this is the projection of the, how will we use it, right? Projection matrix. It's clear? Or so I'm just getting in details a little bit. So most important, I'm doing the same thing as we did in the PCA, just in the new space. And all the difficulty of the kernel, because we don't have the file explicitly. We have to use the kernel, nothing else. Always I'm doing the same thing. The same idea in terms of calculation, I'm forcing it to use the kernel value. Okay? So look here. We find now U1 is this one, right? We prove it, right? So it is linear conversion of this. Okay? U1, what is U1? Is a function multiplied by, you see the function here, multiplied by Ci. Correct? So look here. How to write this one here as matrix product? Phi of x times this one here, right? There is typo here. What is it? Or it is correct or not? Here phi of x is a matrix, right? So it's correct. There's no typo. Okay? Clear? Okay. Now, okay. Look for example here. If you want to do, as we said here, the projection of this one, we get this one is here. Okay. Let me do here again in the calculation here. Let's call this one x, j. What is here, please? X, j. Okay. Okay. I'm looking just for this value here, please. What is this value here? Here we multiply u1 t times xj, right? What is u1, please? u1 is the sum of ci xi transpose times xj, right? And what is this one here, please? The sum over I, ci, and this is the kernel of xi, xj. So here we have here I, yes or no? Okay. What is the product here, please? The product here. The product of this one is lambda n times cj. Look here. What is this relation here, please? I'm writing cj in terms of this one. So at the end, we have this one here. I put it here in the blue. N lambda cj equals to this one. And what is this one here? Is ci multiplied by kernel and this one. So what is here? What are you saying? So, okay, can you tell me here what you can find out here? Lambda, n lambda times the vector equals to the kernel matrix times the vector. What does it mean? Sorry? Lambda n is the eigenvalue of k. C1, C2, C3, the vector is the eigenvector for k. You see, this all is unknown. So in order, now look at, in order to find the eigenvalue and eigenvector for the covariance matrix, which is almost the same like the eigenvalue and eigenvector of the kernel. Because kernel we have it, we can calculate it. As simple as that. You see the idea? Everything what we did to reach this one here. So now, if I'm looking for the eigenvalue, eigenvector for the covariance matrix in the new space, it's better to use the kernel. Look for the eigenvalue and eigenvector of them. But the only difference here, the eigenvalue for k is n lambda, and the eigenvalue for the covariance matrix is only lambda. So just you multiply or you divide by lambda together the thing. So for example, if you get the eigenvalue for k is 5, what is the eigenvalue for covariance matrix? 5 divided by n.
Doctor?
Yes, sir.
Does it mean that C1 has the highest value, and this will be multiplied by k, so we will get the main feature?
Yes, exactly. Yeah, exactly. Yeah. Excellent. Yeah, because this is the idea. Okay.
We found this is similar again. Can it be like we would find out every lambda the same?
Lambda the same. Yeah, no, lambda for lambda 1 for.
I mean, what if the eigenvalues are the same as we are doing this?
Okay, exactly. Yeah, good questions. For example, we did kernel and we find the eigenvalue are almost the same. We cannot compress well. What does mean? Your kernel function is not suitable. Do another kernel. Check another one. There is investigations. Yeah, I agree with you. I totally agree with you. Yes. So, for example, either you are making the things too complex, or maybe your function is not enough. For example, kernel quadratic, do 3, 4, 5, do better. If it doesn't work at all, means there is something wrong in your data. Try to clean it, remove outliers, something like this. Okay. Sometimes we have to do another techniques to use it too. So this is what I'm saying. Look here, please. This is the blue one, is the most important. U1, lambda 1 are the eigenvalue and eigenvector for the covariance matrix. We cannot calculate it directly, but C1 and the Cn and we call it zeta 1, it is lambda 1 n are the eigenvalue of the k, and k we have it. Clear? Yes? So here, for example, what is the, if you have C1, C2 until Cn, what will be mu1? You remember mu1, what is mu1? Mu1 is just linear combination of the Ci of xi. If you have this vector here, we get it from k, kernel functions. You do linear combination, you get your u1. But we don't need it explicitly. So all what we did, we need this one in the blue. What we did, I just to giving ideas. Yes?
The eigenvalues have to be greater than 0.
Yes, correct. Yes. Always eigenvalue are bigger than 0. Why? Because the matrix covariance matrix is positive. And I told you also define positive. There's some technique in linear algebra. Define positives means eigenvalue is positive, strictly positive. It can be 0. Yeah, we call it semi-defined positive. Yeah, not defined positive, semi-defined positive. I don't want to go in details of it, but you can check it in small definitions.
It can be 0.
It can be 0. Yeah.
But if it is 0, it will not do anything.
The 0 is my target to get it. Is this my dream to get everything 0? Only one lambda is bigger. Mean I compress everything in one dimension.
Means all the other lines are like points.
Exactly, point. Means not point. Means is the projection. Yes, 1 point. The projection in this eigenvector is 1 point. Exactly. Yeah. And this is our target, right?
Yeah, because the eigenvalue is like the scale of which.
No, the eigenvalue is. Look, the eigenvalue is the variance of the data on the projection on this eigenvector. You get it? For example, here. This is a good point. For example, this is my, look at, this is my direction, right? This is my direction, and this is my data. Yes? If we do the projection, we get a new value, right? Yes. So, this is eigenvalue 1. The variance here is lambda 1. So if you are forcing lambda 1 or lambda 2 to be 0, what does mean 0 variance? I mean all the points are the same. And this is what we want exactly.
Can you have the break in 5 minutes, please?
Okay, yeah, but we go. For Salat is
Yeah, it's
total.
after 40. Yeah.
I want it before, so we can.
Total Salat.
It's only.
5:43.
We can take like.
Let's take 5
15
minutes just to
or-
rest after we do a little bit. We have the break for Salat.
Yeah, it's better to be on Maghrib.
Yeah, yeah. So all what we were talking here, let me summarize again. Okay. Why we are using PCA, please? Who can tell me? Why PCA? To linearize, good. Or looking for what? Looking for new bases where the variance are bigger in certain directions and really small in other directions. Why the variance is small? Mean all the projections are almost 1 point, so they don't give me any extra information, I can remove them. Clear? Some cases you apply it, but you get all the eigenvalue are important. I cannot summarize it. What does it mean? My problem is nonlinear. What I mean nonlinear? So I have to create more features and try to find a better basis where the information is located only in the few directions, right? You apply kernel functions to make things simple, but time to time, maybe one or two kernel functions does not work, so we have to find a better one. Maybe it doesn't work, we have to do another compression differences, okay? There's other techniques, now we are limited only to the PCA. Clear? So now, where we go to the new spaces, a new spaces is so complex, as I show you with exponentials, we cannot find it explicitly. We use the kernel trick in order to do the projections, and we find out, this is the summary. This is the most important. So, to find eigenvalue, eigenvector to the covariance matrix is impossible, because we don't have phi. What we do, we can calculate the kernel matrix. Easy, we can do it. So we can find the eigenvalue and eigenvector C. But here there is one thing is different. Who can tell me? What is the dimension of K? N by N. What is the dimension of covariance matrix? M prime, the new things, right? So what does it mean here? Maybe the number of eigenvalue of K, they are not the same as eigenvalue of this, right? But we wish maybe we need only few of them, right? We take only R small, the minimum then N, and the minimum then M prime. So what I'm saying here, it is not totally right, because a certain, here maybe N, take example N is 1000, take for example M prime is 2000, right? So the first 1000 eigenvalue and eigenvector are the same, but the others are not, okay? So it is not totally correct, right? But when the number is bigger, both of them are really huge, your data is bigger, your M prime is really huge, so we are almost sure that the information is located at the first 200, 300, 10, 20, we don't know, up to the case. Clear the idea? Okay.
Doctor, what is the sum of the eigenvalues of the kernel?
Sorry?
The sum of the eigenvalues of the kernel. Is it equal to 1?
Maybe, we don't know. It's case by case, we cannot say. We don't know, honestly we don't know. It's up to case by case. But most likely, we want that the information are located in the minimum number of eigenvalues. Okay? Let me go. So this is all what I was proving. You can look to it. But what I'm saying is the same thing, I'm just repeating in a different way. So this is the summary here, please. Okay. You have x1 and xn. We want to compress it to alpha, right? 20%, 30% as we did. What you need to do first? Compute your kernel matrix. What the kernel matrix is? K, xi, xj. And should be given maybe polynomial, maybe quadratic, maybe exponentials, whatever. We shift everything to the 0. We call it k prime. Okay, right? We want to find the eigenvalue and eigenvectors. You see here for k, not for the eigen, not for the covariance matrix, because we proved before they have the same. We find C here, matrix the C1, C2, Cn are eigenvector for everyone. Capital C is matrix. This is diagonal matrix. We have the zeta 1 until zeta n are the eigen value for k. So what is the eigenvalue for the covariance matrix? We divide by n. Is here. Did you put it here or not? Yeah, please, I have to add it later on. Yeah. You remember what we did here, please? Where it was? Yeah, here. This is Z, okay? So just you divide it by n, you get your length, okay? Now, we want the vector to be unit vector, right? So the unit vector here there is a typo. Most of the books, they use the same error, I don't know why, but you can remove it, okay? So here it should be only this one here. Ci, the new Ci, when you get to Ci, you multiply it by square root of zeta I in order to force the unit to be, the vector to be modulo 1. And after you compress it, as we did before, you increase you increase R until the first time you justify or you verify this inequality. Okay? And here what we do, we need only the first R eigenvector. And here the new space or the coordinate, for example, if you want to do the coordinate on the UI, it will be this one. You multiply it by K and so on. So at the end, the new matrix Y, it will be equals to Y1 until YR. It is just this matrix, I keep only the first eigenvector R, and this is all 0, 0. You multiply it by your kernel matrix, you will get a new data set. And the new data set, what is the dimension here? N times R. And R here should be smaller than M, the initial M. Otherwise, all what we did is useless. Okay? But because we want to reduce from M to R. So what we did, M, we go to M prime too big, and after we decrease it again to R. So if you find your R is bigger than M, so what you did is useless. Okay? So our target is, at the end, R should be less than M. Get the idea here? So I give you just the flavor how to prove it, how to do it. I give another way how to prove from A to Z. I put it in PDF file. I think I uploaded it. You can just check it, please. And if you have a question, I can help you more. So all the target now is two things. We cannot find this one explicitly. We use the kernel. In order to do this difficulty, all this one to avoid it, instead of tackling the problem directly to the covariance matrix, we go to the kernel matrix. Nothing else. So later on what we do, we have the data, we do the projection on U1, the projection on U2, or U3, until UR. And the others are not important for us. Okay, so just the idea. Look, for example, this one here. The first one, it is circular. If you apply a kernel matrix, or PCA, it doesn't work. All the lambda are the same, exactly the same. Okay? But if you do it in the kernel, look what we have here. For example, here, if you want to do the classification later on, you need only the x-axis, not the x. What is the x-axis here, please? Represent what, please? The x-axis here is U1, yes or no? Is the direction of the first eigenvector in the new space. Yeah, thank you.
I just wanted to ask, so the eigenvectors are my axes in the new dimension.
Yes, exactly.
So if I have 3D, 3-dimension, I should have 3 eigenvectors.
Yes, exactly.
So here it's like we have 2 dimensions.
Yes,
And we have only 2.
exactly. But here we have 2 dimensions, right? But here, if you look to the variance, yeah. But look here, for example, next to this one, to the new space. What is the eigenvalue on X? Roughly, the eigenvalue on X is bigger or less than eigenvalue on Y. What do you think? What does mean eigenvalue? Mean?
Greater.
Variance, the same thing. Eigenvalue is a variance. So the variance on X-axis when you do the projections, or the Y when you do the projection, which one is bigger? X-axis is bigger because there is no, it is not consistent. So it's more, they are far to each other, so right? And here, if you want to do the classification, it is enough to give X. So what does it mean? If you give me here X, I can say if X is positive is green. If X is negative is blue. Done, finished. So I need only one information to do the classification. But here, give me X and Y, I cannot. So here you can use with, but look here we use PCA, a kernel function. It is not smart way. But here, if you use R, the radius, x squared plus y squared, I need only 1, 2, directly. And the variance will be, in the others is 0, and in 1 is too big. But we call it handcrafted features. And kernel is, I don't know if we call it black box features or, yeah, we can call it black box because we don't know explicitly what is it. You got the idea? here, just example for this one, if you have data like this, and you apply a kernel for a classification, it is not the right thing to do. Okay? So this I'll come back to it later on. Let's do this one, please. I give you this one, try to solve it. So now I give you two questions about PCA and kernel PCA. Okay? We have defined a projected vector x parallel by this one, v times vt times x. First of all, do you think the formula is correct? I didn't ask to prove it, but do you think it's correct or not? You want to project x on v. This is my unit vector v, right?
No, it's not.
So please, v here is 1. Here you have a x. Yes or no? When I do the projection, what I have here, please? I have this one, I call it x parallel to v, and this we call it x perpendicular to x. The way to call it, right? How to find this one here, please? As I told you now. We did it just before, right? So this one for sure is
V transpose.
direction of v. What is the modulo here is vt x. So it's as simple, right? So this is direction, this is the module. Clear? You can do by cosine as well. So the questions here, where x and v are the unit vector along the principal axis, show that the difference vector between the data this and this is orthogonal. So they want to prove that this one is orthogonal to this, or this one is orthogonal to v. Can you try, please? How we can prove orthogonal, please? The dot product is 0, right? So I want to prove that x minus x parallel, if I multiply it by vt, should be 0, right? I have to prove it, right? Should be 0 or not. If it's equal to 0 is orthogonal. If not, okay, let's do it here. What will be here? Vt x, right? Minus vt x prime. This is vt x minus v. What is x parallel? Is given, right? Is vt x. Yes or no? Yes? What is this value here, please? What is this one here? Is value or vector?
Vector.
Value. It is the modulo of? And is equals to 1. So what will be here? In 1 we can remove it. Yes? So what will be here, please? Vtx minus Vtx. And yes, for sure is 0. So yes, they are perpendicular. So you have to observe a few things, right? And why they are orthogonal? Why they are orthogonal? Because we want to minimize the error. And the measure of the error is the short distance is always when we have the orthogonal projection, right? So I just prove it here. The same thing, just giving more explicit. Try to do this one and we go for the break. Just try to solve this one here. We still have time, right? Just tell me before. Look, for example, here. This is for the kernel of the power 2. Look what we have here. We have 1, 2, 3, 4, 5, 6. So we went from dimension 2 to dimension 6. Bigger, right? In this specific example, we have explicitly 5. So we can calculate the covariance matrix directly without using the kernel. Mean just apply PCA on the new data, and it will be like kernel PCA. Clear? So kernel PCA, it is exactly PCA, just on the new space, nothing else, please. Okay? So the idea here, okay, for X is a feature map from this one. So here, what is the, if you do the power 3, what will be the features? If you do the power P, what will be the number of features? Can we find like a rule for that? So the first one we did it, I think we did it in the last section, right? Yes, how we did it, please? Do this one here, product, plus 1, power 2, expand it, try to write it, and you find the same thing, right? Shall I do it with 3? So is it easy question? Here? Just calculation, right? Tell me yes or no? No. No. Let's do it here. Okay. How to find explicitly here, please? Here x1 and x2. Okay. Let's call, for example, the vector here is x1 and this is x2. And call another vector is y1 and y2, right? Okay? This is the vector x and this is the vector y. So what is the kernel? What is kernel x and y, please? Is phi x times phi y. And in this specific case is 1 plus xt y squared, right? So I need to do decomposition of this to get this one. Let's do it here, please. What is it? Let's time this, please. 1 plus x1 y1 plus x2 y2 squared. Clear? Please, can you help me to do decomposition of this? The power 2. 1 squared plus this squared, yes? Plus x2 squared, y2 squared, plus this time this one is 1, x1, y1, plus x2, y2, I think, right? Plus this time this, x1, x2, y1, y2. What else?
Plus x2, y2 multiplied by 1.
There is 2 here, right? 2 here, right?
Yes.
Yeah, something like this, correct? Now, I want to find 2 vectors like this, yes or no? What is it, please? I can say this one, it is exactly the product of 1 times 1. Let me write it here. What is phi of x, please, here? And here phi of y, right? But here only x1 and y2, and here only y1 and y2. So 1 with 1 is here. Second one, x1 squared with y1 squared. Next one. This is done. This is x1 x2 y2 squared, right? Here x1 y1, but the 2 here, how to split it? Square root of 2, square root of 2 the product, right? And so on, the same thing. So we can prove that equals to this one. You can change to the order, huh? Doesn't matter. So you see here how it's difficult? This is only for power 2. If we have different kernel, so it's better to don't bother yourself of it. Okay? If you solve it for power 3, look at for power 3, we get this one here. We get around, so here, the dimension of this one for P1 is 3. Do you agree with that? Is it 3? Because if I remove the square, if I remove this square, what will be here, please? If I remove the square here, remove the square, what will be here? 1, x1, x2, so it's 3. If we do 2, we get 6. If we do 3, we get 9. So do you think we can say for every p, we just multiply by 3? Clear the idea?
Multiply by 3 or
Look it. Can you find a rule here? If P is 1, is 3. If P is 2, 6. If P is 3, is 9. So if P is 4, 12. That's all. So it's up to you when you want to reach, right? So for example, you do 2, still you didn't get better. Try 3, try 4, more higher polynomial, right? Okay. Done. So we stop here. So please try to I give I post the idea behind it, but try to understand it if I can help you. But the most important now is, if we summarize all what we did in PCA, the target is to reduce the dimension of what? Number of features. It's very important, huh? Because number of samples is fixed. We can apply PCA. How to apply PCA? You have to get eigenvalue and eigenvector of the covariance matrix. To calculate the covariance matrix, you have always to subtract the mean. Try to make the mean 0, right? And we can compress it if certain lambda are small relatively to the biggest eigenvalue. If you are not able to find though, try to use a kernel functions. Mean we are going to the higher dimensions or going to different space, and we try to do the compression there. Okay? So all this one we do.
Doctor, the kernel function only apply to the points where there is projection, 90s and
Yes. Yes. Exactly.
We can apply that on there is like
Yeah,
45 angle.
because all the eigenvalue, they are all perpendicular to each other. So if example, if you take only 2, it's like you are doing the projection of the data on orthogonal on this space. Yes. From M to M. Or from M to R. So it's always orthogonal projections. Why orthogonal projection? To minimize the error. Because all the eigenvectors are perpendicular to each other. Otherwise, we are not in the orthogonal projection. Okay? So this is why the eigenvalue of the covariance matrix is always positive or 0, and the eigenvalue are perpendicular. So it's facilitate the task for us. Because if the eigenvalue are not perpendicular, it will be a little bit difficult way to deal with. Okay?
What if we give the dimensions which are not like orthogonally superlative? What will we give in
Because all what we want in the PCA, it is linear, either in the new space or the old space, and all they are perpendicular. So in this, we are lucky in this. But if you have other
But
study,
the old space that we were before here for kernel, it was not linearly superlative.
yes, but the eigenvector